All right. Hi, everyone. Good afternoon. Thank you for joining us. I am sorry that I am on Zoom. Again, I'm actually quarantining for another 48 hours, I think. I came in contact with something, not COVID, but something else my kids were generous enough to bring home to me. Um, we have a presenter today, Dr. Dave Klinges. And so he is currently a postdoctoral associate working with David Skelly in the Yale School of the Environment after receiving his PhD through SNRE in August of 2024. Dave's past work includes agroforestry and restoration in southern Peru, monitoring forest loss via remote sensing at the Smithsonian Conservation Biology Institute, and compiling a coastal carbon database also at the Smithsonian. And at Yale, his work has been more recently turning to forecasting pond hydrology and phenology of the wood frog in Connecticut. For his PhD, he focused on exploring the importance of microclimate for ecology, as he'll discuss today. So, Dr. Dave, thank you so much for being here with us.
Hi, yes, thank you, Allison. I really appreciate those kind words. And I thank everybody for being there in person today, which sadly I am not as well. It's always a bit more fun to be there in person, but I'm think it should be a nice time today. So I'll jump right into it to talk about the roles of microclimate in biogeography across scales. So, to start with a bit of context, we've been monitoring climate at global scales for about a century now to generate maps such as this from the climate product ERA5. And we can use such global climate maps to generate forecasts of possible future scenarios of climate change. Now, these climate maps and forecasts, they're both derived from weather stations, such as this one, all of which are placed in flat, open locations, far away from trees and from hills and other such environmental features that create environmental noise. And if you want to monitor climate in a standardized way across the planet, this is perfect. You don't want any of that noise. But the thing is, that noise and climate is what matters for life on Earth. Almost every species has its own habitat with a distinct microclimate. And let's unpack what I mean by microclimate. So here's a weather station, like I provided in the prior slide, which is measuring macroclimate, air temperature and other variables 2 meters above the ground with no influence on environmental features. But for a bird like the Andean cock of the rock, which lives inside forests, this macroclimate is not going to be representative of the conditions it experience. Forests are typically cooler and more humid during the day than conditions outside of forests. And what's more, even inside forests, we can also have microclimate gradients, such as with height. Typically, it's cooler towards the ground, while in the canopy, it's warmer and more thermally variable. But even outside of forests, we can have microclimatic gradients, such as if there's a patch of barren surface, even right below the weather station, those barren surfaces can absorb solar radiation, get superheated 5 to 10 degrees Celsius hotter than just a couple meters above. This is where perhaps there might be ants that are foraging or defending their colonies. Soils too have their own microclimates, and they're typically less thermally variable than above ground conditions. So this is a mosaic of possible microclimates, all of which are found just a few meters from each other. And this is a key concept that I'll be exploring in my talk. Now, even once we have identified the microclimates important to a given species, there may be disparate responses to climate. Each species has a thermal niche, which is bounded by the coolest and warmest conditions that it can tolerate, typically with some optimum temperature in between those two. And we typically use some form of simple quantitative model, such as a thermal performance curve, that indicates the thermal niche of this organism. how performance changes with temperature. Now, such thermal performance curves, they may differ across species or even across different populations of the same species or individual organisms. They may have different optima, and they may also have a different shape, either a higher or lower optimum or a broader or more narrow thermal breadth to the fish. And so this is another challenge that we face for understanding ecological responses to climate. And so my research program attempts to understand how individual processes such as physiology and microclimate exposure propagate up to the landscape scale, and then understanding shifts in species distributions at broad scales and through time. And for today, I'm going to talk about a couple of projects that are explore three different main themes with this program. First, I'm going to talk about several theoretical projects to better define the scales of climate as relevant to ecology and ecosystems. We're then going to dive into some empirical fieldwork using amphibians in Madagascar to apply these microclimate insights to biological communities. And then we'll scale up to the global level and attempt to remap climate exposure or microclimate as actually experienced by life on Earth. So starting first with one of these theoretical approaches. This is my first chapter of my PhD, and I was interested in revisiting a classic ecological study by Dan Jansen, published in 1967, Why Mountain Passes Are Higher in the Tropics. Some of you may be familiar with this study, but as a brief recap, Jansen's mountain hypothesis was like this. Take a mountain, any mountain, and it's likely to be warmer at low elevation and cooler at high elevation. Now, applying this to a real mountain that Jansen studied in Costa Rica, here is the thermal profiles for low elevation temperatures and high elevation temperatures that Jansen actually studied in Costa Rica. Note consistently that low elevation is warmer than it is at high elevation. What this entails is if there is an animal that lives at the bottom of this Costa Rican mountain, it's likely adapted to only these warm conditions. And so if it aspires to be a mountain climber and try to disperse across this mountain, it probably can't tolerate that cold mountaintop conditions and would not be able to cross the mountain. But take another mountain that Jansen studied in Colorado at temperate latitudes. Here again is the thermal profile at low elevation and at high elevation. And in Colorado, we have seasonality to temperature, so that the coldest temperatures in winter at low elevation are far cooler than the warmest temperatures at high elevation. I'm going to go ahead and provide a laser pointer. Here we go. So now that at the bottom of the mountain, it gets far colder in winter than it does in summer at the top of the mountain. And this entails broad thermal overlap. And it looks like I have to be, there we go. Broad thermal overlap of the mountain in Colorado. So for a species that lives at the base of the Colorado mountain, it has to withstand cold winters and should be able to safely climb and cross this mountain. Now, Jansen's mountain passes hypothesis has been pretty pervasive in biogeography and demonstrates the importance of latitude for thermal overlap across mountains. But we were interested in exploring what other types of geographic factors besides latitude may shape thermal overlap. For instance, microclimate might be important. As an example, you may have a forested mountain, and within this forest, there's different vertical microhabitats, canopies above, and forest understories and soils. And as I mentioned in the introduction, there can be a gradient across this vertical space where there's broader thermal variability in the canopy. Now, applying this to a mountain that we studied in North Carolina, here's soil temperatures at low elevation and at high elevation. Now, soils are thermally buffered, and this entails low thermal overlap across elevation. Then if you look at the temperatures in the forest canopy at the same locations, canopies have broader thermal variability at both low and high elevation, And this entails broader thermal overlap across elevation. Now, this is just data from a single mountain that we studied, but for our paper, we compiled about 500 years of temperature data from 29 mountain ranges globally to then explore the importance of different geographic factors across scales. So, we calculated three different mathematical scores of thermal overlap. I won't get into these scores today. And then we explored several different gradients across scales. Latitude being a macrogeographic gradient, three intermediate factors of the change in elevation, meaning that the height of the mountain itself, the amount of vegetation on the mountain, and the amount of snow that the mountain received. And then we looked at a microgeographic gradient, which was the height or depth at which the thermal logger was placed. This is our forest soil versus forest canopy comparison of the prior slide. And I fit linear mixed effects of models and average coefficients across these models to derive this set of results. Now, let me unpack these for you. First, starting with change in elevation, the height of the mountain. It had a significant negative effect on thermal overlap. That means that taller mountains tend to yield lower thermal overlap, which is pretty intuitive. Taller mountains are going to have broader thermal gradient and are therefore harder to climb. But now let's look at latitude, which was Jansen's hypothesis. Tropical versus temperate, all the way up to polar mountains. And we found that latitude actually had a non-significant effect on thermal overlap. Rather, it was conditions on the mountain that explained more variability. For instance, the amount of forest on the mountain. Forested mountains tend to have lower thermal variability and entail lower thermal overlap. But then also we looked at the microgeography, the height or depth of the thermal logger. We found that this had a significant positive effect. And what this means is if there's an organism found in the understory or soils, such as what we illustrated in the prior slide, they're going to experience narrow thermal overlap and would have a hard time climbing mountains. Conversely, organisms adapted to canopies with broader thermal variability should be able to more easily climb mountains. So, revisiting our question of hand, what besides latitude was important? Well, we found actually latitude was not a very important predictor at all. The macrogeographic gradient may not actually be that important for thermal variability. Altitude, the change in height of the mountain itself, was, as we expected, quite important. But there might also be this overlooked gradient of vertitude, the height above ground or depth below ground that an organism's microhabitat is. And in fact, a 1 meter shift in vertitude yields a change in thermal overlap equivalent to over 600 kilometers in latitude. So this synthesis stood as one of the most comprehensive reevaluations of Jansen's mountain passes hypothesis to better untangle scales of climate. But as my colleagues and I started thinking more about climate across scales, we realized that ecologists, we somewhat lacked an understanding of how to define the scale of climate in the first place. There's a couple different scales that different dimensions by which we can define scale of climate data. One might be the spatial resolution of climate data. It's perhaps intuitive that coarse grain climate data is less fine scale than fine resolution climate data. And then the same might apply for temporal resolution, where moving from monthly climate observations to hourly climate observations, that's an increase in scale, and it might be more useful climate data. But resolution in space and time, it may not explain the whole picture of climate scale. For instance, if we take a mouse that lives below ground within forests, and I hope you guys can see my cursor. I think you can, because I'm pointing at different places. If we understand climate exposure for this mouse, what climate data product will be better? Fine resolution macroclimate data or coarse resolution climate data that represents forest understory conditions. The second climate product, although it is coarser resolution, might have relevance to this mouse. And we call this relevance proximity, which we proposed in our paper as the third dimension of climate scale. So for this work, we wanted to see whether resolution in space or time, or proximity of climate data, better improves ecological predictions. And for this, we used three different climate data products. WorldClim with high spatial resolution, ERA5 with high temporal resolution, and Microclimate, which is a mechanistic microclimate model that can represent proximal conditions. Now, just to briefly unpack what microclimate is, it's a mechanistic model, process explicit, that was developed by my collaborator Ilya McLean at the University of Exeter. And these mechanistic approaches entail that the energy going into a system must equal the energy going out. For this, we provide gridded estimates of climate forcing data, solar heat, radiation, precipitation, that are then influenced by local landscape features such as vegetation, topography, and soil composition that are handed as parameters to the model to predict microclimate through space and time. Okay, so we had three different climate data products, each of which we applied to three different ecological case studies. The first is tracking the spatial distributions of mosquitoes. The second was modeling the phenology of an insect crop pest. And the third was predicting range shifts through space and time of a salamander species. And for the sake of time today, I'm only going to be able to talk about a third case study on salamanders. So for this case study, we looked at how the salamander species Plethodon jordani shifted its range in the Great Smoky Mountain National Park, the only place that it's found on Earth. And we were interested whether high resolution macroclimate data or coarse resolution microclimate were better at predicting salamander range shifts. So for this, my lab mate and colleague Alex Becker constructed species distribution models for the 1960s and 1990s for the salamander species that we fitted to empirical observations of the salamander in the park. And I'll note that for both of these models, I won't go into detail too much about their performance metrics, but they both had rather good fit to our salamander observations. We then derived the spatial differences in these two different SDMs between the 60s and the 90s to derive an estimate of range shifts of the salamander across this 40-year period. And we know for a fact that these salamanders were indeed shifting their ranges from low elevation to high elevation over time. But which of our climate data products would best predict these empirical range shift tracks? Well, so we used our three climate data products and we fitted generalized additive models of climate change across time from Microclimate, WorldClim, and ERA5. So these represent three different climate data products, each of which we modeled climate change at different spatial resolutions. So 12 different possible models, each of which to compare to our empirical salamander range shifts. We want to see which of these 12 did best. Well, we looked at the portion of variance explained by each of these models, starting first with ERA5, which is a macroclimate data source. ERA5 had an R-squared value of about 0.2 across all spatial resolutions. WorldClim performed a bit better than ERA5, but Microclimate, our proximal microclimate model, really took the prize, especially at fine spatial resolution. It explained nearly 60% of all variation in salamander range shifts. But furthermore, Microclimate at 3 kilometer resolution outperformed WorldClim and ERA5 at 1 kilometer resolution. So this entails that, yes, coarser grain microclimates did better than fine grain macroclimates. Now, returning to our question at hand, this entails that increasing spatial or temporal resolution is good, but perhaps increasing climate proximity is better for understanding ecological impacts. And that entails that defining microclimate is more than just high resolution climate data. It's knowing the distinct microhabitats that your organism occupies, which is system specific knowledge. Right, so these were two theoretical projects to better define the scale of climate data. And I now want to apply these to understanding biological communities in reality. And for this work, I visited one of the most biodiverse nations on the planet, which is the island of Madagascar. Madagascar is known for its high rates of endemism and biodiversity, and its amphibian communities are no exception. There's over 400 amphibian species that have been identified so far in Madagascar, over 99% of which are endemic to the island. But unfortunately, there's been high and fast rates of deforestation, especially in eastern Madagascar, over the past 50 to 60 years. And this has proved a large challenge for conserving this mega diversity of amphibians in Madagascar. Now, for understanding how microclimate may influence forest amphibians from the ground up into the canopy entails actually visiting the forest canopy, where a lot of amphibian species are found. And so we monitored microclimates and surveyed amphibians from the floor to the canopy. I don't know how well these videos are rendering, but uh, searching for amphibians in the forest canopy is similar like it is on the ground. You're looking through leaf litter and through plants. One of the differences being that you're hanging from a rope about 30 to 40 meters above the ground. So as a result, it's a part of the animal community that is not sampled that often, but poses a really nice system to explore microclimate variation across this vertical forest gradient, as well as exploring how amphibians that occupy different temporal niches might be influenced by microclimate. For instance, during the day in forests, it's much warmer than it is at night. And we found amphibian species that each occupy distinct temporal and spatial niches across the forest vertical gradient and in day and night. And this posed this high richness and number of animals that we found in Madagascar. It provides a nice system by which to study basic questions in thermal ecology. For instance, how thermal niches differ between species, and especially how their selected temperatures, their preferred temperatures, which may be most closely linked to their optimal temperatures. Why do different species have different optimal temperatures? Well, there's some prior work that would suggest that species that occupy warmer conditions, thereby warmer microclimates, would have warmer thermal preferences. This is called coadaptation. It's rather intuitive. If I live somewhere warmer, I probably prefer it warmer. Conversely, we may also find a pattern of a negative correlation between environmental temperatures and thermal preferences, meaning if you occupy a warmer microenvironment, you actually prefer it cooler. Now, this might seem counterintuitive, but it may be that species that are living in cooler conditions are actively seeking out warmer spaces and times than what the mean conditions would suggest. And a countergradient pattern suggests that thermal regulatory behavior is quite important for animals. So we wanted to see whether a co-adaptation or countergradient pattern was expressed for this amphibian community. Which temperatures are preferred by rainforest frogs relative to the mean conditions they experience? So for this study, we tested the thermal preferences of frog species experimentally using chambers like this, where each one of five had a single animal placed in it, and there was a hot end and a cool end, and the animal was allowed to choose where its preferred temperature was. We then combined this with mechanistic microclimate modeling of forest temperatures in space and time, both from the floor to the canopy and day and night separately. And I'll quickly note that our microclimate model used here had pretty good performance. Here, these gray points on the right are observations of temperatures in space and time, and these are our model predictions. So this model allowed us to predict temperature across many different heights in the forest and across time continuously, where we were not able to monitor temperature. And we wanted to see whether these amphibians expressed a positive correlation between the microclimates they occupy and their thermal preferences, or a negative correlation. And here's our empirical results, which was a slight negative correlation, demonstrating a counter-gradient pattern. And this counter-gradient pattern was even stronger for arboreal species, those only found in the forest canopy. So this first shows that thermoregulatory behavior is indeed important and runs counter to the environmental gradient. We were also wondering, well, why do arboreal amphibians have a stronger kind of gradient pattern? Even though they are only active during the day, they prefer they only active at night. They prefer temperatures that are far warmer than what they occupy in the forest canopy at night. Now, it might be that arboreal animals are not active during the daytime because there may be a larger proportion of predators. Oh, excuse me. They may be able to tolerate the warmer conditions of the day, but cannot tolerate the drier conditions of the day. And our microclimate model confirmed that it was indeed drier during the day. It may also be that arboreal amphibians are not active during the day because they have a higher proportion of predators, such as birds, that would be preying upon them if they were active during daytime conditions. And therefore, they are only active during their uh, during nocturnal times. Now, what was interesting is this pattern of not finding arboreal amphibians during the day entails warm and thermal niche underfilling. They are not active in all of the warm conditions by which they can tolerate. And this warm and thermal niche underfilling, it reflects some of the findings that prior studies have had across elevation gradients and across latitudinal gradients, all of which demonstrate warm and thermal niche underfilling. So revisiting our question here, we found that rainforest amphibians demonstrate a counter-gradient relationship of their thermal preference with the mean environmental temperatures they experience. And this emphasizes the importance of thermoregulatory behavior, as well as suggests thermal niche underfilling across scales. Now, I'm just going to quickly mention some projects that I will not be able to discuss in detail today, but when engaging in abroad, especially in majority world locations, it's really important to get involved with capacity building in conservation. And I've really had a privilege and an honor to collaborate with some colleagues at Madagascar National Parks to understand what pathways by which we can improve wildlife monitoring in protected areas in Madagascar. And I'm going to skip that slide. And then finally, after these two themes that we've explored of better defining the scale of climate data and then applying this improved definition to empirical biological communities, I then wanted to scale things up using computational approaches to remap global climate as experienced by life on Earth. And one of the most universal applications of global climate data is the Köppen-Geiger climate categories. These delineate climate zones across the planet based upon temperature and precipitation as measured by weather stations. Now, Köppen-Geiger climate zones, as derived in the past, have been using macroclimate data. But what if we remapped Köppen-Geiger across the planet using microclimate data? So for this study, we did exactly that. We compared Köppen-Geiger climate categories, where they were found and what categories they were, from a climate source of ERA5, as well as a microclimate model, Microclimate, for 32 million locations across 6 continents. But for today, I'm not going to be able to talk about these all. So I'll just highlight a couple of different case studies, starting with Myanmar and southeastern China. So in this region, here are the predictions of Köppen-Geiger zones using macroclimate. Each of the different colors represents a different category of climate. And here are the predictions for microclimate. So first off, frequently there were differences in what a given location was classified by macroclimate versus microclimate. But beyond this, microclimate classes were also more spatially variable. This means that for a given location, macroclimate may have fewer classes, such as 14 classes here, relative to microclimate, which had 18 in the same spatial extent. Microclimate classes were also more accurate. They had lower error by 14-fold than the macroclimate predictions. And furthermore, microclimate also suggested broader latitudinal distributions than macroclimate, suggesting that there are cool microrefugia at low latitudes, as well as warmer hotspots at high latitudes. Now, I had to breeze through these results today, but let me illustrate an application of these results to a societal use here in the Pacific Northwest. Now, here are our Köppen-Geiger climate predictions by macroclimate on the top here, and then microclimate below for the same spatial location. And now let's actually look at the true land use for the same region in the Pacific Northwest. This is a map of what crops are planted across this area. And I'm going to highlight in particular three crops that are cash crops in the area: apples, grapes, and hops used for brewing beer. This region is especially important for these three crops, and the Pacific Northwest in the United States accounts for 99% of all of the beer hops productions in the US and 25% of all beer hops production globally. Now, these three crops, they are planted primarily in some of these areas I've indicated with black rectangles. And farmers in the area have learned that these three crops thrive best in dry conditions that have lower disease pressure. The Köppen-Geiger zone that represents these dry conditions are these two categories, BWH and BWK, which are the orange pixels in these two maps. I'm going to make these two maps a bit bigger. So the orange pixels is where we should find the crops as predicted by the Köppen-Geiger zones, and the black rectangles are where they were actually found. Macroclimate was not predicting the suitable climate really in any of the locations where we were truly finding crops, while microclimate had spatial patterns that better reflected the true land use of where these crops are planted. So this is one application of why microclimate data may be useful in a broader societal application. And revisiting our question, we did find that microclimate was more variable, more accurate, and possibly more useful. Now, given the possible importance of mapping microclimates across space and time, my colleagues and I decided to put our efforts together and develop a novel set of microclimate maps at the global scale, representing near surface and soil conditions, which we call DIRTCLIM. And here's a map of mean annual temperatures of DIRTCLIM across the planet. But it looks about the same as any other global climate map. So let's zoom in to a location that we're all familiar with to better illustrate some of the potential of DIRTCLIM. So here's satellite imagery of Gainesville, Payne Prairie below it, and a broader agricultural context around the city. Now, this here is a map of average temperature by WorldClim, which is a popular macroclimate data source. But now here is DIRTCLIM predictions from the same temporal region. You can note that DIRTCLIM predicts much warmer conditions in the city of Gainesville itself, as well as in areas such as the tarmac of Gainesville Regional Airport, while cooler in some of the forested areas around the city. So DIRTCLIM is representing high resolution land use across Central Florida. To provide another example of the potential of DIRTCLIM, this image on the left is satellite imagery from southeastern Brazil in the arc of deforestation. You can see where forest has been clear cut in the southern part of the scene. And here's DIRTCLIM predictions from the same area. which is denoting warmer conditions where forest has been cut down. So dirt clim can be useful also for tracking the thermal fingerprint of human land use. Now, dirt clim is not just static maps in space, but it's also time series, hourly predictions across 20 years. And for this, we can maybe not just understand microclimate, but micro weather. And from these high resolution climate predictions, we've derived a set of bioclimatic variables, such as annual mean temperatures for 20 years, but also some indices of extreme conditions, such as the annual maximum temperature, the amount of time per year below freezing, and the frequency of heat waves here across the continent of Australia. And there's more than just temperature and thermal variables in dirt clim, but also hydric variables, such as soil moisture across time. Now, you might be wondering whether we can trust these maps. Well, I won't be able to fully dive into validation today, but just very quickly, I'll note that we conducted a comparison of dirt clim's performance to two macroclimate products, WorldClim and ERA5, and compared all three of these model predictions to about 600 thermal measure loggers from the database soil temp from 4 different continents. We found that the average bias of WorldClim and ERA5, the macroclimate products, were above 3 degrees Celsius, while DirtClim had average bias about half of that, 1.7 degrees Celsius. So we think that dirt climate is probably trustworthy, especially for soil and near surface conditions. And at the moment, we are pursuing several manuscripts with dirt clim, but we're going to make the database publicly available soon. And please do reach out if you are interested in using some of these data. And just to illustrate one quick example of how we have used some of these microclimate models for which dirt clim's derived, we have a recent publication in Nature Climate Change evaluating how much climate novelty have tropical rainforests experience across the planet. So to recap for today, we had 3 different broad themes to explore the roles of microclimate. We first started with a couple theoretical studies revisiting Jansen's mountain passes hypothesis to show the importance of microgeography for shaping dispersal of organisms through space, and also better defining the scale of climate data with the axis of proximity. And this entails the defining the climate scale of species and systems of interest is pivotal for knowing how you use climate data. We then visited Madagascar to apply several empirical studies of microclimates to therefore understand how organisms choose their thermal environments. And therefore, we should probably choose wisely where we monitor and when we monitor temperature as well. We then scaled up to the global level, reevaluating Köppen-Geiger climate categories, as well as developing a novel database of microclimate in space and time, to therefore measure climate locally as actually experienced by life on Earth, but then to think and apply these products globally. And with that, I will thank my core collaborators, as well as many other teammates, and colleagues, friends who have helped along the way, especially my collaborators and team in Madagascar, who helped collect a lot of these data, as well as my committee members. And I'll then thank you all today, and I'll happily take any of your questions.
Thank you so much, Dr. Dave. That was really, really interesting. And yeah, we can open this up to questions either in person or online or in the chat. Actually,
As
if it's
far
okay,
oh,
I'll just jump
sorry.
in with a question, which is just sort of a more general question. I was wondering if you could talk a little bit about sort of how you got interested in the field, how you kind of came to focus on this for your PhD.
Yeah, thank you, Allison. That's a good question. And early on, I had some lucky exposure to a few colleagues who had gotten excited in trying to scale up insights that ecologists have been thinking about for a while, which is that the climate data that meteorologists have been developing, it's really useful for meteorology, but it's just rarely going to reflect what most species experience. And, and I think anybody who's gone and done field work probably has thought about this a little bit, where wherever you may be conducting biological or agricultural or natural resource monitoring, it may not be similar at all to where the local weather station is. To
Mm,
answer your question, I got excited by this because I'm exposed to a couple of the modeling approaches that made scaling up these insights possible
mm.
across broad regions in ways that have not been possible for decades. So it was just kind of a lucky time for me, um, where ecology has been kind of right based upon the new software and models that have been available.
Dave, I think you're muted, maybe.
I am muted. I was finishing up answering the question, and I was
Okay.
just trying to reduce the background noise.
Yeah, I got you. Okay, okay, okay. Thank you.
As far as number one in the mountain passes, did you guys ever think about looking longitudinally as well, like with rain shadow effect and stuff like that?
That's a really good idea. And to be honest, we didn't think formally about the rain shadow effect at all when conducting this study. Um, I, from what I recall when I was pulling the data together, I tried to standardize the slope and aspect and cardinal direction of the temperature data that I'd been using. But I don't recall whether I explicitly controlled for precipitation gradients. And for those unfamiliar, rain shadow effect being if there was a predominant trend of synoptic weather, so weather coming in from one direction, a mountain range will be a barrier to that weather, those clouds. Clouds will rise and they will drop all of the rain only on one side of the mountain range, so the other side's a lot drier. But I think that's a really good point because you have plenty of mountain ranges. I can think of several, like the Sierra Nevadas in the US, where it's highly vegetated on the wet side and not very vegetated on the other side. And that absolutely could be asymmetric differences in species dispersal on either side. So no, we didn't. I think there's a lot of data out there that could explore this more explicitly, and it would be a really cool follow-up that I think is worth exploring.
Awesome, thank you.
Any other questions? Okay. All right. Well, I want to remind everybody that Dave's contact information can be found on the flyer if you do have a question that you want to follow up with. Um, Otherwise, Dave, thank you so much for that presentation. That was wonderful, very, very enlightening. And to everybody else, thank you for being here. If you had anybody has any questions for me before next Monday, obviously get in touch with me anytime. Otherwise, I hope everybody has a great rest of their week.
Thank you, Elson, and thank you everybody for being here today.
Thanks for joining us.